Welcome back to the deep dive. You sent us a fantastic stack of sources on a topic that's pretty essential, but often flies under the radar. We're talking about a revolution happening inside our factories, integrated machine safety controls. For the industries you follow, this shift is, well, it's everything.
It really is.
When we talk about machine safety, I think most people just picture, big yellow cages or those emergency shut-off buttons.
Being a big red button, yeah.
Exactly. But this deep dive is about what's next. It's about merging safety functions directly into the machine's actual operational code.
And that's the mission here.
Right. So the goal is to finally get rid of that old mindset where safety always meant slowing down production.
That's the critical pivot we're unpacking for you today. We are looking at the specific components that don't just act as physical barriers, but actively communicate with the machine's control logic.
Things like e-safety devices, smart guarding.
Sophisticated e-safety devices, physical guarding, and centralized logic systems, exactly. And the goal for any company investing in this technology is really twofold. You get robust operator protection, and you simultaneously optimize your production workflows.
But there's a bigger impact here, isn't there, for the industries you're watching?
Oh, absolutely. I think the biggest practical impact is this. These integrated solutions are the primary custom way that companies all over the world bring these huge fleets of older legacy machines up to current, really strict international safety standards.
Without having to replace them entirely.
Without having to replace them, that's the key.
So the stakes are extremely high. We're talking about efficiency gains measured in millions and human protection measured in, well, in lives. To understand how they pull this off, we have to look at the philosophy of it all.
Let's unpack that integration.
Yeah, let's do it.
The foundational philosophy is, in a word, unity. System unity. Traditionally, safety was its own thing, a siloed function.
Right. You had your machine control over here, and then you bolted on a separate safety relay system over there.
And they didn't really talk to each other. Integrated controls just discard that whole approach. They embed the safety functions directly into the machine's main programmable logic controller, the PLC itself.
So there's all one brain.
It's all one brain, and that allows for communication, for diagnostics, and most importantly, for verification.
Okay, so if the core idea is that safety has to integrate, what are the tangible benefits? Why is this so much better than the old way of just, say, installing a limit switch that physically cuts power when a door opens?
It's all about speed and intelligence. A traditional safety system, like that switch, often resulted in what we call a nuisance trip.
A nuisance trip.
Yeah, the machine just stops entirely. Maybe a sensor got a little dusty, or a door alignment was off by a millimeter.
And then you have to call maintenance, reset everything, and you've lost valuable production time.
Exactly. But an integrated system, because it can diagnose and verify, knows exactly why the process stopped. It can often allow for a quicker, smarter restart. Or it might even just slow the process down instead of a full, abrupt, and sometimes damaging stop.
So it improves that key metric, OEE operational equipment effectiveness.
Drastically. Because the machine spends more time running efficiently. Safety stops being this anchor holding back your OEE and becomes a necessary diagnostic part of it.
Okay, so to get that level of integration, you need specific custom systems. You've identified 6 core types for us.
That's right. And let's start with safety in the most dangerous zones.
The places where even a tiny spark could be a catastrophe waiting to happen. Tell us about those.
That's where intrinsic HAZLOC-rated safety systems come in. HAZLOC is just short for hazardous locations.
So areas with explosive gases, dust, flammable fibers, that kind of thing.
Precisely. And in those places, the safety challenge isn't just stopping the machine. It's making sure the electrical circuits that power the machine or its sensors can never generate enough heat or energy to cause an ignition.
How do they even do that?
It's purely preventative, right down at the circuit level. They operate using these low-energy, intrinsically safe circuits. The voltage and the current are limited to levels so incredibly low that even if you get a short circuit or if components fail, they just can't store or release enough energy to create a spark.
So it's not hot enough to ignite the atmosphere around it.
It's safety engineered right into the physics of the system itself. It's absolutely crucial for, chemical plants, milling, petrochemical industries.
That's a fundamentally different way of thinking than just a guardrail. You're controlling the hazard before it can even exist.
Exactly.
So building on that idea of verification, what about that really critical moment of making sure a machine is truly stopped before an operator goes near it?
That brings us to our second type. Zero-speed detection systems.
Yeah.
It's so easy to look at a huge machine with a heavy motor and just assume it's stopped when the power is cut.
But there's still inertia, coasting.
A lot of it. A large rotary component might still be spinning for several critical seconds, and that poses a huge crush or cut hazard if an operator reaches in too soon.
So just relying on a simple timer or listening to see if it's quiet
Yeah.
is, well, it sounds extremely risky.
It is. A zero-speed detection system actively monitors the motor's rotation. It uses specialized sensors to verify what they call definitive zero-speed conditions.
So it has to read absolute zero.
Absolute zero, and only once the system confirms that motor rotation is zero, which is usually indicated by a dedicated safety relay, only then does the safety circuit allow the interlocks on the doors to open for maintenance.
Without that verification, you're just gambling with residual momentum.
You are. And that brings us to the third system, which is where it gets really practical. You're mixing electronics and mechanics. The intelligent physical guard.
The vertical safety door.
Exactly. These are just vertical sliding doors that give you safe, compact access. They're great for tight factory floors because they don't swing out and block walkways.
But their safety isn't just about being a physical barrier. They're integrated.
Right. They use sophisticated interlocks. The machine's control logic knows the exact position of that door at all times. If the door is open, the machine cannot cycle. That's obvious.
Sure.
But an integrated system can also monitor other things through that door's status, like, is the air pressure correct? Is the lubrication system for the machine inside ready? It won't allow a run command until all those conditions are met.
So a simple physical guard becomes a smart input for the entire control system.
That's integration.
Okay, that covers the passive safety and the smart physical guards. Let's pivot now to systems that require direct, intentional human input.
High-stakes stuff.
Yeah, where the operator is interacting with the machine right up until the point of operation. These are actuation scenarios where a tiny mistake, a lapse in judgment, could be disastrous.
And the ultimate example of this is the two-hand control system. These are mandatory for certain high-risk machines like presses, where the point of operation is directly hazardous.
And the core requirement is that the operator has to press two separate buttons at the same time to make the machine cycle.
Correct. It forces the operator's hands to be safely outside the danger zone.
I get that part. But the sources we looked at really emphasized a critical feature, the anti-tie-down safety relay. Why is that specific component so vital?
It's vital because operators are ingenious when it comes to finding ways to speed things up, even if it means bypassing safety.
Ah, the tie-down hazard.
Exactly. It refers to an operator using a piece of tape or a clamp or even a heavy tool to hold down one of the two activation buttons.
So they can use one hand for activation and the other is free to load material, putting it right in the danger zone.
And that's how severe injuries happen. The anti-tie-down relay prevents this. It continuously monitors the timing and the sequence of the body presses. If those buttons aren't actuated within, say, a fraction of a second of each other, the relay locks out the system.
So you can't cheat it.
You can't. Or if one button stays down after a cycle, same thing. It locks out. It demands that both hands are physically present, engaging their controls simultaneously, ensuring the operator is fully clear.
That insight really underscores why integration is so much more than just adding a switch. It has to anticipate human behavior and engineer solutions to get around those shortcuts.
Absolutely. Which brings us to probably the most recognized intervention system of all.
The emergency stop or e-stop device.
The big red mushroom button?
Everyone knows what that looks like.
Yeah.
But inside an integrated control system, what is its function beyond just turning the machine off? How is it designed to be the ultimate fail-safe?
An e-stop isn't just an off button. It's an immediate, guaranteed shutdown of hazardous motion, and it's designed to bypass pretty much all normal control logic. It has to adhere to the highest reliability standards.
So it's on its own super important circuit.
Essentially, yes. It triggers what's called a Category 0 or Category 1 stop. Category 0 is just an immediate, uncontrolled power removal. Everything just cuts. Category 1 is a controlled stop, like a fast deceleration, before the power is removed.
And crucially, it has to be fail-safe.
It must be. If the wiring to the button is cut, or if a component inside that circuit fails, the system has to default to a safe, stopped state. It absolutely must work under all circumstances.
And for context on these interaction systems, we should probably quickly mention the sources also highlight grip-enabling switches, or deadman switches.
Right. Those are another type where operation depends on sustained operator action. Think of the handles on a commercial lawnmower.
If you let go, the blade stops.
Exactly. In industry, if an operator loses their sustained grip on that enabling switch, the hazardous motion immediately halts. It forces constant conscious interaction to keep the machine running.
So we've covered controls for hazardous atmospheres and controls focused on operator interaction. Now, let's shift to what's arguably the most specialized and complex area, guarding extremely powerful equipment, like industrial presses.
This is where you need specialized equipment, specifically things like light curtains and mechanical backups.
Presses and press brakes are just immensely dangerous because of that crushing force.
They are. And simple physical barriers are often impractical because the operator needs frequent access to load and unload material. So this is where an invisible barrier, safety light curtain, becomes essential.
Okay, so how does that work?
A light curtain uses an array of photoelectric sensors. It creates this high-density grid of invisible infrared light beams across the opening. If any part of the operator's body breaks that light barrier, a hand, an arm, the safety circuit immediately sends a stop signal to the machine.
And it halts the dangerous motion before any contact can be made.
That instantaneous reaction time is key.
I noticed our sources specifically mentioned the difference between standard and profiling light curtains. They used examples like the ProTech Eagle Eye. What's the functional distinction there?
That's a great question, and it really speaks to how sophisticated these systems are now. A standard light curtain just guards the access point, like a flat plane. A profiling light curtain, which is often high-density infrared or even camera-based, does more. It doesn't just look for a break in the plane.
It can dynamically profile the shape of the tool or the die.
Exactly. And this means the machine can distinguish between the operator's hand and the actual material being fed into the press.
So it's smart enough not to trip just because the workpiece is entering the zone.
Right. It allows for closer operator proximity, which supports faster feeding and unloading, all while maintaining that high safety integrity. The system recognizes the difference between a hand and the material and only stops when an unexpected profile, like a human limb, enters the zone.
The evolution in this technology is just incredible. We saw a state-of-the-art example in the source material, the laser-safe Sentinel Plus press brake guarding system. How does laser technology build on that?
Laser systems, especially for press brakes, offer an even higher degree of precision and intelligence. The Sentinel Plus, for example, it uses a laser zone that constantly projects this protective field very close to the point of operation.
But it's more than just detection.
Oh, much more. It features automatic alignment, so the laser adjusts in real time as the tooling changes. It also has real-time monitoring and speed analysis of the closure.
So it's constantly checking and rechecking.
Constantly. And this combination ensures enhanced safety, but because the system is so precise and so adjustable, it minimizes those nuisance stops, which leads to maximum productivity.
So you've got these incredible electronic protections, infrared and laser barriers, super fast, super sophisticated. But we always talk about layers of defense. What happens if all that electronic control logic fails?
And that's the big question.
Which brings us to the mechanical backup system, die safety blocks.
This is so important. When you rely on high-speed electronic logic, you absolutely must have a mechanical plan B. And die safety blocks, or die block interlocks, are the non-negotiable physical fail-safe for press maintenance.
Describe what they are.
They're essentially just heavy, often brightly colored, solid pieces of steel. And you place them directly between the upper and lower dies of the press.
So they mechanically block the die.
They physically prevent accidental press closure. This is paramount during setup, maintenance, tooling changes. It ensures that even if power is restored by accident, or the control logic glitches, or an e-stop is reset when it shouldn't be,
the operator is protected from that crushing hazard by a big chunk of steel, by immutable physics.
Exactly. Sheer physics.
That detail really crystallizes the whole concept for me. The integrated system demands redundancy. It verifies zero speed electronically, but you still need a piece of physical steel to mechanically guarantee the safe state when a human is inside.
That's the whole philosophy.
So what does this all mean for you, the learner? The key takeaway here is that modern machine safety isn't a static list of compliance rules. It's a dynamic, comprehensive, embedded logic system.
It really is.
And it's designed, from the circuit board all the way up to that massive steel block, to bring existing legacy equipment up to modern standards. And in doing so, it makes production safer and, paradoxically, more efficient than it ever was with the old bolt-on equipment.
We've seen that every single component works together to achieve safety through integration and verification. whether it's verifying zero-speed conditions before allowing entry, or demanding that simultaneous two-hand engagement with an anti-tie-down relay, or precisely profiling the work zone with lasers.
The system is proactively ensuring safety and maximizing machine uptime.
It's doing both at once.
And that layered approach, that ability to rely on both electronics and mechanics, is what makes these systems so robust.
Yeah.
We saw how die safety blocks provide that critical, purely mechanical defense, even when the complex electronic logic fails.
It's the ultimate backup.
So here's a final thought for you to mull over. Given this reliance on advanced electronic controls like laser systems and anti-tie-down relays, what mechanical systems might be next to require a mandatory physical, pure fail-safe override? As automation moves toward collaborative robots and highly mobile equipment, consider what happens when a piece of software fails, and why human proximity will always demand an independent physical defense. It's definitely something to think about as you see automation continue to grow and evolve.
It's a great question to end on.
Thank you for joining us on this deep dive into integrated machine safety controls. We'll see you next time.